Welcome to my channel. Today I'm teaching you how to find modular multiplicative inverse. So let me just write the topic first before we proceed. Modular multiplicative inverses. Now I'll teach you how to find modular multiplicative inverses using one, the Euler theorem, and two, the Fermat's. I want to use Fermat's little theorem. Fermat's little theorem. Then I'll use the extended Euclid's algorithm. So these are the three methods I want to use to get the modular multiplicative inverses. Now, what is very important in today's video is that I'll use these three methods in the same, for each question, for you to see, in the same video, for you to see when do you use the Euler theorem, when can you use the Fermat's little theorem, when can you use the extended Euclid's algorithm. Because there are cases where the Euler theorem may not work. There are cases where the Fermat's little theorem may not work. And there are cases where I prefer using the extended Euclid's algorithm. So you need to know when are we to use each of these methods. And that is what is very important in today's video. Now, so I'll begin by the statement of the Euler theorem. I'll begin by stating what Euler theorem says, so that we now then see how do we use it to find inverses. So let's begin by the Euler theorem. Now what Euler theorem says is that now you'll try and check the exact statement of the theorem, but I just want to mention the important parts of the theorem. It says that if a is a positive integer, and p is another positive integer, relatively prime to A, then a raised to 5p would be congruent to 1 mod p. Now it's good to note the conditions here. The condition here is that a must be positive integer, and that p must be another positive integer which is relatively prime to A. What that means, what the word relatively prime means here is that the GCD of this R and P must be 1. That is, the GCD of A and P must be 1. That's what I mean by relatively prime. So this is the statement of Euler theorem. And as I said, I was just mentioning what is important in this theorem. The conditions here, that this must be relatively prime to R. And if that happens, then this will be correct. This will be correct. Now, so I do not want to go into how to find the Euler 5p, because I believe that one you already know, that the Euler 5p, how do you get it? if P is prime, then the Euler, if P is prime, then the Euler phi of P, you know that it will be given by P minus 1. But if P is not prime, then you must ask yourself, and there are so many ways of finding the Euler phi of P. There are so many ways of finding that. So if P is not prime, then the only question you need to ask yourself is how many prime numbers can divide P? For instance, now how many prime numbers can divide P? So if you discover that n is a prime number, m is another prime number, and w is another prime number, which can divide P, then the Euler phi of P will be given by 1 minus 1 out of n multiplied by 1 minus 1 out of m multiplied by 1 minus 1 out of w multiplied by P. Just give a small example. I'm not seeing what I was writing. Why did it go to? Did not save. When I stopped sharing, it disappeared. So I've already said that if you discover that the prime numbers n, m, and w divide, if these prime numbers divide P, then the Euler phi of P will be given by 1 out of n from 1 multiplied by 1 minus 1 out of m multiplied by 1 minus 1 out of w multiplied by P. And so, of course, you know that when we talk of the Euler phi of P, we mean the numbers less than P which are relatively prime to P. The numbers less than P which are relatively prime to P. The numbers like, for instance, if P is 16, then we mean the numbers which are less than 16 and are relatively prime to 16. In fact, these numbers are just 1, 3, 5, 7, 9, 11, 13, and 15. 1, 2, 3, 4, 5, 6, 7, 8 numbers. 8 numbers. So that means Euler phi of 16 is 8. In fact, this formula helps you to get the answer 8 without necessarily having to list the numbers and counting them. So for me to use this formula, I'll ask myself, which prime numbers divide 16? Which prime numbers divide 16? So the prime numbers that divide 16 is just 2. Therefore, the Euler phi of 16 would be 1 minus a half multiplied by 8. No, that's 16, which is a half multiplied by 16, which is 8. So this is how I get if P is not prime. Now, so what is very important is we've already shown how to find what the statement of the Euler theorem, and we've already said that Euler theorem says that a raised to 5p would be congruent to 1 mod p. And that for us to find the inverse, when we multiply this equation by A inverse, we found that we would have, when we multiply this equation by inverse, by inverse of A. We want to find the inverse of A. So when we multiply by inverse of A, we have inverse of A multiplied by A phi of P is congruent to multiply this side also by A inverse, would have A inverse mod P. And so these are indices on the left side, gives us A raised to phi of P minus 1 is the inverse of A, mod P. So this is how we find the inverse using the Euler theorem. What this means is that if you're given an equation AX, congruent equation, AX equals to C mod, the AX is congruent to C mod P. If you're given the equation, the congruent equation, AX is congruent to C mod P, and you are asked to find the value of X, you only need to make X the subject of this formula by multiplying both sides by the inverse of A. And the inverse of A is this. This is the inverse of A. So you just need to multiply this side by the inverse of A. So the inverse of A P minus 1 multiplied by AX, not P minus 1, multiplied by AX will be congruent to A raised to phi of P minus 1 multiplied by C mod P. But now you know that this is A times its inverse, which will give us 1. And so the result on the left side is X is congruent to A phi of P minus 1 multiplied by C mod P. So this I will be finding X. In one of our videos, in our next video, we'll be looking at equations. And this method will come in. And again, in that video, we'll be looking at various methods for the sake of comparison, so that we can know when do we use this method and when do we use the other method. We shall have several methods in that video. Now, so if you're given a congruent equation, then this is how we'll be solving it. X will be given by this. Now, let me look at the Fermat's little theorem. And because we'll be using it to find inverses. But this is very important to us. This Euler theorem gives us this for finding the inverses. The Euler theorem gives us this for finding the inverse. So we'll be seeing when do we use this. And we've already said we can only use this method if P is positive, A is positive, and P is relatively prime to A. What about Fermat's little theorem? Fermat's little theorem. What does it state? Fermat's little theorem states that if A is an integer and P is a prime number, a prime positive number, a positive prime number, prime integer. If A is an integer and P is a positive prime integer, which does not divide A, then A raised to P minus 1 will be congruent to 1 mod P. And there are very many conditions here that are very important. The first condition is that P here must be positive, must be a prime number, positive prime number, and that this P should not divide A. This P should not divide A. And if this condition is met, then A raised to P minus 1 will be congruent to 1 mod P. These are the important parts of the Fermat's theorem. That's what it states. Now, how do you find this? How do you use this Fermat's theorem to find the inverse of A? So I want to call this equation 1 and multiply that equation 1, multiply 1 by the inverse of A. So when I multiply by the inverse of A, then 1 becomes, I'm multiplying by the inverse of on both sides. So times A P minus 1 is congruent to the inverse of A mod P. What you notice is that we have, these are indices, the base is the same, so we would have A raised to P minus 2 being congruent to the inverse of A mod P. And this is how we'll be getting the inverse using the Fermat's theorem. What again this means is that if I'm given an equation Ax is congruent to B mod P, then X will be, I just want to multiply both sides by the inverse, and this is the inverse, and so that will give me B multiplied by A P minus 2 mod P. That is how we'll be finding the value of X. And as I said, that will be in another video when we'll be looking at how to solve congruent equations. And we'll be using Fermat's theorem, we'll be using the Euler theorem, and again we'll be using the extended Euclidean algorithm. Now, let's now look at examples of finding modular inverses. Examples. And let's look at 2 examples, and in these 2 examples, I'll use the 3 methods so that we can learn how to use which method and at what time. Now, so the first one I want to do is I want to say find 56, the inverse of 56 mod 97. So that is the question. Find the inverse of 56 mod 97. Now, the Euclid's algorithm can work for any of these questions. Will work for any of these questions. So I want to begin by the Fermat's theorem first of all. Fermat's theorem says that P here must be prime and it should not divide 56. If P is prime and cannot divide 56, then Fermat's little theorem can be used. And so by Fermat's theorem, by Fermat's little theorem, so I'm doing it first by Fermat's little theorem, and then I'll do it by Euler the Euler theorem, then I'll do it by extended Euclid's algorithm, that you can know how to use each of those methods. Now, by Fermat's little theorem, the inverse of 56 will be given by 56 raised to P minus 2. P minus 2, our P is 97, minus 2 will be 95. Mod 97. So that is how we find the inverse. It will begin by 56 raised to 97 mod 56 raised to 95 mod 97. So we're just asking ourselves, what will be the remainder if this number here is divided by 97? So the remainder when this number is divided by 97 will be the inverse of this. This is what it means. This is what it means. We just want to find out what will be the remainder if this number is divided by 97. So there is a very easy way of doing that. We just form a square table, and we ask yourself, what is 56 raised to 1? It's mod 97. 56 raised to 1 will be 56 mod 97. What about 56 raised to 2? 56 raised to 2. 56 raised to 2 is the same as 56 raised to 1 times 56 raised to 1. Actually, it's the same as 56 raised to 1 times 56 raised to 1, which is just, but 56 raised to 1 is 56. And 56 raised to 1 is another 56. Mod 97. So you're asking yourselves, what's the remainder if this number is divided by 97? So when you use your calculator, and just use your calculator, I also have mine here. When you multiply this number and divide by 97, the remainder will be 32. The remainder will be 32. Now, what about the square of this? The square of 56 square. The square of 56. The square of 56 square is 56 raised to 4. So 56 raised to 4 is the same as 56 square. The square of 56 square. But 56 square is 32. So the total of 32 square mod 97. So what's the remainder when 32 square is divided by 97? And that one, you just use your calculator again. I have mine here. When I do mine, and I'll be getting 54. We just take 32 times 32, then divide by 97, then write the remainder here. The remainder is 54. Now, I also want to get 56 raised to 8. I'm just squaring, just getting the table of squares. So 56 raised to 1, 56 square, the square of that, the square of this. So the square of this will be 56 raised to 8, which is the same as, and if you've been following, that will be the same as 54 times 54 mod 97. We're asking ourselves, if 54 is multiplied by 54 and divided by 97, what will be that? What will be the remainder? So again, use your calculator and you find that the remainder will be 6. What about the square of 56 raised to 8? 56 raised to 8, the square is 56 raised to 16, which is 16, 6 times 6 mod 97, and this is just 36 mod 97. So you can write mod 97 if you want mod 97. It's understood that we are already working with mod 97, so that's why in some cases I'm not writing. What's the square of this? What I'm looking at is 56 raised to 95. So I'm trying to square and square until I get 56 raised to 95. So 56, the square of this is 56 raised to 32, which will be 36 square. And when you do that using a calculator, you would get 35. You get 35. And then let's also square this. 56 raised to 64. 56 raised to 64 will be 35 square mod 97. So what is the remainder when 35 square is divided by 97? And when you do that, you get 61. So you notice that if I square this again, I would have 56 raised to 128, which is beyond what we want, because what we want is 95 as the power. So we try to use what we have here. We try to use what we have. Let me just do it here because let me just do it here. So 56 raised to 95, we use what we have, will be the same as 56 raised to 64. So I'm looking at which of these numbers, if I add, I get 95. So I can see that if I have 64 plus 16, that would be 80, plus 8, that would be 88, then plus 4, that would be 92, 92 plus 2, that would be 94, plus 1, that would be 95. So I'm just using my squares here. 64. I discovered that when I add 64 and 32, that will give me 96, and so it will be beyond. So then I use the smaller ones. 64 plus 16, that is 80. 80 plus 8 will be 88. 88 plus 4, that will be 92. 92 plus 2, that will be 94. 94 plus 1, that will be 95. And so what this means is I have 56 raised to 16 times 56 raised to 8 times 56 raised to 4 times 56 raised to 2 times 56 raised to 1. And I know what 56 raised to 64 is. I know that is 61. I also know that this 56 raised to 16 is 36. I also know that raised to 8 is 6. Raised to 4 is 54. Raised to 2 is 32. Raised to 1 is 56. So you multiply with your calculator this and see what to get. Let me just clear this space here so that we can use it. Let me clear some space here because we already used to this, we don't require it. So when you multiply this with a calculator, and remember it's mod 97, you find that 56 raised to 95, when you multiply with your calculator, 61 times 36 times 6 times 54 times 32 times 56, using my calculator I'm getting 127, 51, 51, 6, 8 mod 97. Don't worry about how I am writing slanting, there's no problem. But this is just one number. This is one number. This is what you get. So the question is, if I take this number and divide by 97, what will be the remainder? And I'm finding the remainder to be 26. What that means is that the inverse of 56 mod 97 is 26 using Fermat's little theorem. So using Fermat's little theorem, this is what I find as the inverse. Let me use the Euler theorem in my gain arrays and use the Euler theorem. So B, I want to use the Euler theorem. To find the inverse, Euler theorem says that a raised to phi of p minus 1 will be congruent to 1. Now will be the inverse. Will be the inverse. Just a minute. What it says that the inverse of A will be given by this mod P. So that means that the inverse of 56 will be given by 56 raised to phi of 97 minus 1 mod 97. But what is 597? 97 here is this number is prime. This number is prime. So if it's prime, we know that 597 is 96. And then that means that this inverse will then be given by 56 raised to 96 minus 1, which is 95 mod 97. So when you reach here, then you proceed the same way we did for the Fermat's-Little theorem, because for the Fermat's-Little theorem we also found that the inverse was given by this, and then we proceeded from here to find the squares. So that means that for this question, then the Euler theorem and the little Fermat's theorem agree that the inverse will be given by 56 raised to 95. Now let's now use the last method, which is the extended Euclid's algorithm, to find the inverse. And as I said earlier, the extended Euclid's algorithm will be used for any of the questions to find the inverse. But the Fermat's-Little theorem, you must check P to see that P is prime and that P is relatively prime to R. You look at our conditions earlier. And for the Euler theorem, you must check that P and R are both prime and that they are relatively. No, they are both positive and they are relatively prime. So let's use the extended Euclidean algorithm. Or the extended Euclid's algorithm. Now, for the extended Euclid's algorithm, you look for the GCD of these two numbers, and the GCD of these two numbers is 1 from what I see. The GCD is 1, and so you use long division to find the remainder and then reverse. So what we want for the Euclid algorithm, we want to find that we want to write this as write 56 and 97 in terms of as being equal to 1. 56 times A equals to 1. No, 56 times A plus 97 times B is equals to 1. We want to write this in this form. We want to write 56 and 97 in it. So we want to find two numbers, A and B, such that 56 times A plus 97 times B gives us 1. So in this case, then A here shall be the inverse of 56. A here shall be the inverse of 56. So let's just do long division. We're asking ourselves, 56 goes in 97 how many times? and you find that 56 goes there once, and just subtract 56 from 97, and you find that the remainder will be 41. And then you ask yourself, 41 goes into 56 how many times? So that is 56. 41, of course, will go there once, and the remainder will be 15. You just divide 56 by 41, and then see what the remainder is. Then 15 goes into 41 how many times? And this one is twice, because 2 times 15 will be 30, and the remainder will be 11. 11 goes into 15 how many times? So 11 goes there once, and the remainder is 4. And 4 goes into 11 how many times? 4 goes into 11 twice, because of 8. And 8 from 11 will be 3. And 3 goes into how many times? Goes there once, and the remainder will be 1. And 1 goes into 3 how many times? 1 goes into 3 times, and the remainder is 0. That means 1 is the GCD. 1 is the GCD of 56 and 97. So we want to reverse these equations, make this one the subject, and reverse going up. Substitute going up. So we want to reverse this equation. So the first equation here means 1 is equal to 4 minus 1 multiplied by 3. Let me just put a 1 here because there's nothing here. This. Let me put a 1 there because I can see the coefficient there is 1. So 1 equals to 4 minus this. Now what about, let's substitute 3. What is 3? 3 is 11 minus 2 multiplied by 8. So this is the same as 1 times 4 minus 1. But instead of 3 we've seen is 11 minus 2 multiplied by 11 minus 2 multiplied by 4. Let me just put a 1 here. So what does this give us? Collect like terms. I have negative 1 multiplied by 11. So I'm just multiply this negative 1 inside. Negative 1 multiplied by 11. Then negative 1 multiplied by negative 2 will be positive 2 multiplied by 4. So positive 2 multiplied by 4 plus plus 1 multiplied by 4. That gives us 3 multiplied by 4. This is 1 plus 2 will be 3. Now, so let's substitute 4. We've already substituted this. So let's now substitute this. What is 4? 4 is 15 minus 1 times 11. This will be negative 1 times 11 plus 3. But instead of 4, you're writing 15 minus 1 multiplied by 11. So I hope you are seeing that. This is 1 multiplied by 11. So let's just open that bracket. I'll begin with 3 multiplied by 15. And this other one is 3 multiplied by negative 1, which will be negative 3. Negative 3 plus this negative 1, that gives us negative 4. Multiplied by 11. Negative 4 multiplied by 11. So let's now see what about 11. What is 11? 11 is 41 minus 2 multiplied by 15. So this is the same as 3 multiplied by 15 minus 4. But instead of 11, we know that it's 41 minus 2 multiplied by 15. Yes. Now let's open this bracket, therefore. Then begin by negative 4 multiplied by 41. And then this negative 4 multiplied by negative 2 will be positive 8. Positive 8 plus this 3 will be 11 multiplied by 15. 11 multiplied by 15. Now, so what is 15? 15 is 56 minus 1 times 41. So this is negative 4, 41 plus 11 into, instead of 15 we're writing 56 minus 1 times 41. So let's open this bracket. What do we get? Let's begin with 11 times 56. And then this 11 times this negative 1 will be negative 11. Negative 11 plus negative 4. That will be negative 15 multiplied by 41. Then what about 41? 41 is 97 minus 1 times 56. I'm trying to write small things so that my space can fit, but even if you're watching on your phone, you can try to make it in, you can zoom or even try to have it not, if it is, yeah, if you zoom, I think you can see that. Yeah, if you zoom, you can see that. So I was saying that 41 would be, 41 is 97 minus 56. (97) minus 1 multiplied by 56. And that is the last replacement. So let's now write the result. This will be negative 15 multiplied by 97. And this negative 15 times negative 1 will be positive 15. Positive 15 plus 11 will be 26. So you have 26 times 56. And this is what I want, what we said we will have. What we have now is, what we have is that 1 is equals to negative 15 multiplied by 97 plus 26 multiplied by 56. This is what we began to find. We wanted to write it in this form. And we said that when we write in this form, then our A here will be the inverse of 56. The A there is 26. Hence, 26 is the inverse of 56. It's the inverse. So what that means is that if I multiply 26 times 56 mod 97, the answer will be 1. The answer will be 1. That's how we use the Fermat's theorem, the Euler theorem, and the Euclidean algorithm to do this question. So let's look at another question, and it's the last question that I'll be doing. So the question here is that find 50, the inverse of 50 mod 93. So I want to see which method can I use. I can see that 93 is not a prime number. 93 is not a prime number. So that means Fermat's little theorem cannot be used. Fermat's little theorem cannot be used. And the reason is that 93 is not a prime number. Remember that P must be prime number for Fermat's little theorem to be used. What about the Euler theorem? Can it be used? We look at P and 50 and see whether they are relatively prime. That is, if the GCD is 1. And of course, I can see that the GCD is 1. Since the GCD is 1, it means I can use the Euler theorem to do this question. I can use Euler theorem. And what does Euler theorem say? Euler theorem says that the inverse of this will be given by 50 raised to 5 of 93 minus 1 mod 93. But what is 593? Then I ask myself, this is where we began, and we said that since it's not prime, we would ask ourselves what prime numbers divide 93. And I can see 3 can divide it. I can see 3 can divide 93. And if 3 was to go here, to go there 31 times. So there's another number that can go into that 1. So that 1 is also a prime number. So the prime numbers that divide 93 is 3 and that 1. And therefore, the Euler phi of 93 will be 1 minus a third times 1 minus that 1/3, or 1 minus 1 over 31 times 93. And this is just 2 out of 3 times 30 out of 31 times 93, and this gives you 60. That gives you 60. So that means that the Euler phi of this of 93 is 60. That means therefore the inverse will be given by 50. The inverse therefore is 50 raised to 60 minus 1, which is 59 mod 93. 50 raised to 59 mod 93. So very fast, let's form a square table. Let's form a square table. I want to erase this part. And we form a square table so that we see what is the remainder if 50 raised to 59 is divided by 93. So as we did earlier, 50 raised to 1 is just 50. Remember, it's mod 93. What about 50 raised to 2? It will be 50 times 50, which is 2500. Mod 93, that will give me 82. That will be the remainder when this result is divided by 93. What about 50 raised to 4, the square of this? It will be 82 times 82 mod 93, and the remainder there will be 28. What about 50 raised to 8, which is 28 times 28 mod 93? Let's say this is 28 times 28 mod 93. So we're asking, what is the remainder when this is divided by 93? And I was getting the remainder to be, use your calculator to get 40. What about the square of that, which is 50 raised to 16? That is 40 times 40 mod 93. So when 40 times 40, which is 1600, is divided by 93, the remainder will be 19. What about the square of this, which is 50 raised to 32, which is 19 times 19, mod 93. So when you square 19 and then divide by 93, the remainder will be 82. What we want is 50 raised to 59. So when I square this, I'll get 64, which is not okay. It's beyond what we want. What we want is 50 raised to 59. And we check which one do we add to get 59. So I can see that we can take this 32, can take this 32, then I can see that we can add 16 there to get 48, then add 8 to get 56, then add 2 to get 58, then add 1 to get 59. So I'm just adding the powers so that I get 59. So this is the same as 56 raised to 32 times 56 raised to 16, not 56. It is not 50, it's 56 times 50 raised to 8 times 50 raised to 2 times 50 raised to 1. But 50 raised to 32 is 82. This other one raised to 16 is 19. And this other one is 40. And this other one, so raised to 16 was 19, raised to 8 was 40, raised to 4, no, there's no 4, raised to 2 is 82, and raised to 1 is 50. If you want, you can reduce the larger ones. This large one is 82. 82 mod 93 can write as negative 11 here. You can write this one as negative 11 if you want to reduce your work, and also this one is negative 11. Or you can just work the way they are, but you can also reduce them. But whichever thing you do, multiply what you have here, and divide by 93, and then get the remainder. The remainder will be 80. Multiply what you have here and divide by 93, and then find the remainder. The remainder will be 80. So that means that 80 is the inverse of 50. 80 is the inverse of 50 mod 93. So that means 80 times 50 gives you 1. Now very fast, let's use the Euclid's algorithm. Very fast. I want us to use the Euclid's algorithm. Already we said that the Fermat's theorem cannot be used because 93 is not prime. So the Euclid's algorithm, let's get the recipe, Euclid's algorithm. (93) divided by 50. 50 would go there once, and the remainder will be 43. 43 into 50. 43 into 50 would be once, to go there once, and the remainder will be 7. 7 into 43 to go there 6 times, and the remainder will be 1. And then 1 into 7 go there 7 times, and the remainder will be 0. So 1 is the GCD, so we reverse this, so we write thus 1 equals 43 minus 6 multiplied by 7. So just reversing. And then what is 7? What is 7? 7 is 50 minus 1 multiplied by 43. So when you open this brackets, what you have is this. Negative 6 times negative 1 will be negative, will be positive 6, plus this one here will be 7 multiplied by 43. So what about 43? What is 43? 43 will be 43. What is 43? 43 is 93 minus 1 multiplied by 50. So when you open this brackets, what you have is 7 multiplied by 3. 7 times that will be negative 7. Negative 7 plus this will be negative 13 divided by 50. So now we have that 1 equals this. In other words, what this means is that negative 13 is the inverse. But I want to write this as a positive number. So negative 13 mod 93. I just added that negative 13 plus 93, and that gives me 80. So 80 is the inverse of 50 using the Euclid's algorithm. And that's how you find the inverse using the Euclid's algorithm. And you've also seen how to find using the Fermat's little theorem and how to use the Euler theorem. And you've seen the comparison. What is important, we now know when do we use the Fermat's and where can we not use Fermat's. Where can we use the Euler theorem and where we cannot use. And we've said that the Euclid's algorithm can be used in any of them. So the next video shall be to look at how to solve concurrency questions. If you've not subscribed to my channel, you can subscribe so that whenever I load a lesson, you can automatically receive it. Thank you.